So for perchlorate, it's carrying 5 electrons, iron 2 plus, 1 electron, iron 3 plus carries 1 electron. Why is that? Kind of screwing this up, I'm sorry. Let's try this again. So, sorry. For migration in the bulk, the total amount of current carried in the migration process is characterized by I sub m. And that turns out to be equal to n over the charge, z sub j, times the transference numbers of the species. So for perchlorate, it's 10 electrons times the charge, which is 1 over 1, times the transference number, which is 5/10. And that equals to 5 electrons. For iron 2 plus, again 10 electrons. It has a 1/2 charge times its 2/10 transference number, and so that refers to 1 electron being carried. And for iron 3 plus, same calculation. All right, so in the bulk, what we're saying is that if we have a system that's composed of 2 copper electrodes, cathode and anode, the cathode having a negative charge, anode having a positive charge, 10 electrons are coming in the system, because that's what we said was happening. So we're going to get a current flow for the conversion of iron 2 plus, 3 plus to 2 plus. And at the anode, we'll have the oxidation occurring, so we're going to have iron 2 plus going back to iron 3 plus. So in the bulk, there's going to be a migration effect. And in order to carry that current of 10 electrons, we're going to be moving 1 by the iron 3 plus, 1 electron by the iron 2 plus, and we're going to be moving the ratio of perchlorate, we're going to be having 5 perchlorate ions moving in that particular direction. So in order to carry that current through the bulk, we're going to have a net movement of 1 iron 3 ion, 1 iron 2 plus ion going towards the cathode because they're being attracted to the negative cathode, and then they're going to be moving the other way towards the anode, the perchlorate is. And so you can see there's 5 positive charges moving towards the cathode and 5 negative charges moving towards the anode, thus giving us our 10 electron charge total that we need to have moving through the solution. There is, however, also the consideration what happens at the interface, and here we have to consider a diffusional process. Because the iron 3 plus and 2 plus are being used up at the interface or produced at the interface, now we have some the diffusion effects. At the cathode, what's happening? Well, the cathode is using up iron 3 plus to 2 plus. And the diffusional part of the thing is the total amount of current minus the migration amount. And so since we have 10 electrons of current going in minus the migrational component, we see that the ID is equal to 10 minus 1, or 9 electrons being carried by that iron 3. Same with the iron 2. In this case, the movement is in the opposite direction, so we have 10 plus 1 equal to 11. At the same time, we still have perchlorate ions at the interface that are not diffusing, but they're migrating. So ID is equal to I plus IM, where ID is 0, so we're having a value of 5, minus 5 in that case. Oops. So if we draw at a cathode, we see that coming towards the electrode there is iron 3 plus, and there's essentially 9 electrons worth of iron 3 plus coming that way. There is essentially 11 electrons of iron 2 plus going the opposite way, and there's essentially 5 electrons of perchlorate coming towards the cathode, or away from the cathode. Yeah. So the total charge at the interface is minus 27 because there's electrons going towards the cathode, 22 away, and minus 5. Oh, something is wrong here. The total I have is minus 10. How's this going on? The perchlorate has to be moving the opposite way at the interface to cancel out the charges of the irons moving in and out. At the other thing, the values are basically just changed to the opposite sign because the opposite reaction is occurring. And so there's our 10 electrons coming in at the interface. So at the interface, we've got the movement of charge is effectively 9 electrons of iron 3 plus. The effective charge amount of 9 electrons coming towards the interface, 11 electrons going away from the interface, or 22 total charges, and 5 from the perchlorate to give us a minus 10, and the opposite is going on at the other electrode. Okay. So we can calculate basically the movement of ions in a simple way and see what based on the transference numbers, what fraction is carried by each of the species in solution. Now, if you see here, the perchlorate is carrying most of the charge in the bulk of the system. Actually, because it's singly charged, we're moving a lot of perchlorate ions in this direction. On the other hand, the highly charged iron 2 and 3 plus, only one of those are moving to carry that charge. We can imagine what would happen if we took and added a large amount of an inert material, such as sodium perchlorate, to the system. Now, the large amount of the sodium ions would be moving and requiring much less movement of the iron 3+ at the interface. Again, the diffusion would be still significant at the interface for the iron 2+ and 3+, but the sodium would be carrying the migration part of the currents. Okay. As I said, the migration process is generally not considered to be significant in most calculations of the mass transfer processes. We tend to eliminate the effect of migration as much as possible. In the past few years, however, there has been lots of experiments where migration has been specifically not excluded, really more like 7 or 8 years. Particularly for electroanalysis. Now, in electrochemistry that was involved in manufacturing or electrosynthesis, things like that, migration is often considered as part of the system itself. It's obvious it's going to be in there. But in electroanalysis, we tend to try to eliminate migration. However, migration is not excluded under certain conditions where we have very small currents. In that case, the currents are small enough that the voltage drop due to the solution resistance is very small. So we have small ohmic drops. And that means that we can actually avoid having the sporting electrolyte in the system. That has the advantage that we don't have to introduce impurities, and that can often be an advantage for analysis, where we don't have to add anything specifically, and that can avoid impurities and making the analysis a little bit more sensitive. And these are usually done using what they call ultramicroelectrodes, which we'll talk about later. And they are very small electrodes that allow us to do these sorts of things. The other reason that we're interested in doing experiments without sporting electrolyte is also just to study the physical process of migration and get some physical parameters, and that can be done, again, directly rather than having to indirectly calculate the effect of migration. All right. Well, we'll not consider migration much after this.